In this module, we'll talk about pegmatites, a little bit about trace elements and how they some concentrate in the pegmatites, and compatible and incompatible elements. Pegmatites are these usually very coarse-grained dike intrusions that are the last bits of melt to crystallize when a magma is crystallizing. So whether you're crystallizing a granitic magma or a granodiorite or even a diorite, the pegmatites are going to contain the minerals that are lowest temperature on Bowen's reaction series. And so in these dikes, there's a variety. The upper right one is a good example of some case bars that look pretty abundant in this dike, plagioclase, and those are probably sodium-bearing plagioclases, quartz, and perhaps a few mafic minerals, but the percentage would be very low. That's typical to have these really felsic minerals crystallizing in a pegmatite, and you also get some other less common minerals crystallizing, and we'll look at those in class. So the pegmatites, you're likely to see minerals down at the lower temperature end of Bowen's reaction series because these are the last minerals to crystallize in a magmatic system. So these are crystallizing at pretty low temperatures, 800 degrees and lower, when the pegmatites form. Now, we've mostly been talking about major elements when we're talking about the chemistry of different igneous rocks. And on this chart, you'll see that we've got aluminum, magnesium, iron, calcium, sodium, potassium, and titanium and phosphorus to a lesser extent here. But notice that the percentages of these minerals are relatively high, certainly more than 1%. And that's what constitutes a major element in a rock. And also look, these are the cations compared to how much silica is in the rock. And you'll see that on the left-hand side of these graphs, at 45-50%, these are the basalts on this end. And on the right-hand side, we're at 70-75%, these are the equivalent of the rhyolites. And we were talking a little bit in class about how the chemistry changes from a rhyolite to maybe an andesite and then to a basalt. And these graphs show, these are for a range of compositions of volcanic rocks from Crater Lake in Oregon. And you can see, for instance, in magnesium, there's a steady increase in the amount of magnesium, the amount of iron, the amount of calcium from a rhyolite to a basalt. You see that also in the titanium. You'll see that there's an opposite sense, that there's a decrease in the amount of potassium, the amount of sodium in the alkali elements, so the potassium and the sodium, from a rhyolite to a basalt. And that there's a more complex trend in the aluminum and in the phosphorus. But that's how the chemistry changes from rhyolites to basalts. It's gradual. There's no clear cutoff point where you stop calling one thing a rhyolite to an andesite and a basalt. It is really based on those classification diagrams that I've shown you before. Now, in the pegmatites, we have a lot of trace elements that become more important. And trace elements, if you look at the scale on these charts, you'll see that they're listed in parts per million. So 1,000 parts per million is equivalent to 1%. So these are all less than 1% in a rock. So again, this is plotted against silica, and you'll see, for instance, from a rhyolite to a basalt, the amount of zirconium increases a lot going from basalt to a rhyolite. Nickel, the overall trend is a general decrease in nickel from a basalt to a rhyolite. So there's another process going on here that controls where those trace elements are concentrated. Some of these elements are incompatible, and that means that they tend to stay behind in a melt and not be incorporated into a crystal structure. And what that means is that the incompatible elements are going to be more concentrated in the later stage melts, so in pegmatites and granites that crystallize, rather than the basalts, because those are crystallizing at lower temperatures and at later stages. So these are elements that have a high charge and have a smaller ionic radius. Those include the rare earth elements, thorium and uranium that I'll mention in a moment, zirconium, hafnium. Those are important trace elements in granites. They also include the low field strength large ion lithophiles, and those include we've got a major element, we've got potassium there too, and some other elements that become important for geochronology actually. We also have compatible elements that are relatively small ionic radius and have low valence. And those include, I just showed you nickel. Chromium is another important one that we'll see evidence for in some of these rocks, platinum, gold. If we plot these elements with ionic charge versus ionic radius, you'll see that the incompatible elements fall in the upper right-hand side, and those include what I was talking about before, the thorium, uranium, zirconium. And those are important in granites because if there's abundant zirconium in your granite, you're going to crystallize zircon, ZrSiO4. And thorium and uranium replace the zirconium, or can substitute for the zirconium in the crystal structure because they have a similar charge and ionic radius. And what that does is if we have zircon in a rock, we can extract the zircon and use it to date the rock. So if you want to use the uranium and thorium decay system, so uranium lead dating, then you need to have zircon or maybe monazite, but more commonly zircon, and you need to go find a felsic or maybe intermediate rock in order to get the zircon, because those are the rock types that these incompatible elements are concentrated in. Now, as far as compatible elements, I mentioned nickel and chromium are important. When I talk about ultramafic rocks, I will mention in particular chromium, because chromium is a diagnostic. It helps crystallize a chromium diopside, which is really bright green and found only in ultramafic rocks. And so really early, very, very mafic, ultramafic rocks are going to have the chromium in them. And chromium diopside happens to be diagnostic in picking out a rock called a kimberlite that we'll discuss later. But the compatible elements are those that get incorporated into the crystal structure early on, and you find in the more mafic rocks that are crystallize at higher temperatures near the top of Bowen's reaction series. Okay, what you learned in this module was that pegmatites form last from a crystallizing magma. They're coarse grained and have a relatively simple mineralogy comprised of minerals from the low temperature end of Bowen's reaction series. The trace elements are present in low concentrations, and so less than 1% of the elements in a rock. And incompatible elements prefer to remain in the melt, and so are therefore abundant in pegmatites and granites. Compatible elements are incorporated into the crystals early on at higher temperatures and are more abundant in mafic and ultramafic rocks.